Hello class, welcome to exercise 7G, intersection of lines and parabolas. In this lesson, your examples and pre-learning will be example 14, finding points of intersection of a parabola and a horizontal line. And your pre-learning for this example will be questions 1 and 2 in the new book and question 6 in the old book. And then we'll do example 15, which is solving simultaneous equations that involve a line and a parabola. And your pre-learning for this example will be questions 3 and 4 in the new book and questions 7 and 8 in the old book. Then example 16 is solving simultaneous equations with the quadratic formula. And your pre-learning for this example is questions 5 in the new book and questions 9 in the old book. And then finally, example 17 is determining the number of solutions of a simultaneous equations. And your pre-learning will be question 6 in the new book and question 10 in the old book. So just looking at the amount of examples there, you can see that this is going to be a huge lesson. And this means we're going to be covering a lot of concepts. And we'll be bringing together pretty much everything you've learnt in this unit, plus some things from our linear relations unit. So you'll need to be confident with simultaneous equations, which is a topic that we did cover in linear. And the two concepts from that you really need to bring to this lesson are solving simultaneous equations with substitution and graphing. And if you're not confident with either of these, you really need to pause the video right now and focus on revising exercise 1J. And from this unit, you're going to need to be confident solving quadratic equations, particularly using the quadratic formula. But after doing all the quadratics in the first half of this unit and using the solutions of quadratic equations and the quadratic formula already in our graphing, I'm pretty sure that you will be. Considering everything that we're doing and drawing from concepts from a previous unit, this lesson is really a measuring stick, so I hope you treat it like that to really see how far you've come this year. Alright, we'll see you in the introduction. Okay, here is a parabola and a straight line. Now how on earth are we going to work out the intersections of the straight line with the parabola? So let's cast our mind back to the linear relations unit, and from there we already know how to solve the intersection between two straight lines. So for example, these two lines here, which we could describe as y equals m1x plus c1, and y2, the other line, equals m2 times x plus c2. I'm going to call that first graph y1. Well, obviously, that intersection is where y1 is equal to y2, which when you take into account their formulas, we could rewrite that as m1x plus c1 equals m2x plus c2. And I can rearrange that by putting the x's and c's on each side. And if I want to solve that for x, I'm going to take out the common factor and divide both sides by m1 minus m2. And we've now found the x value for this intersection. And with some luck, that substitution will have some pretty easy numbers. And once we've figured out what that x value is, the next step is to find out what the y value is. But what if we want to find the intersection between a line and a parabola? I honestly feel like it's easier to draw a parabola if I don't have to worry about points. But anyhow. Now, by definition, that parabola is y equals a times x squared plus bx plus c, right? In other words, it's all the points where y is a times the x value squared plus b times the x value plus c. And by definition, the line is y equals mx plus d, which similarly is all the points where the y value is m times the x value plus some c. I mean d, and I've deliberately chosen d so we don't confuse it, even though I seem to somehow still have done that. Anyhow, by definition, the intercepts are where the line and the parabola have the same x and y values. And the easiest way to solve this is using substitution, which I must admit is the one I said not to do so much of in linear. But in circumstances like this, you're going to find that elimination is no good and we want to use substitution. Okay, so to find where y equals mx plus d and y equals a times x squared plus bx plus c. And of course that means the line and the parabola have the same y and the same x. And yeah, and where they're the same means that mx plus d is going to equal ax squared plus bx plus c. Okay, because the y's are the same, and don't forget the x's are the same in here of course as well. And the other way of looking at it is we've subbed in one y value for the other one. Anyhow, at this point, solving for x is now just like solving a quadratic. So if we look at the line above then, if I subtract mx plus d from both sides, we end up with 0 is equal to ax squared plus bx plus c minus mx minus d. Okay, and if I collect like terms now, that's ax squared plus b minus mx plus c minus d. And I've written it in this way because in practice, you won't have two algebraic terms there, you'll have a number that you've done that with. But anyhow, I want to give you a better look of this in GeoGebra. And we can do that by following this link. Okay, so here's a parabola, and here is a line. Sorry if I sound like I'm singing about a teapot. Now you can see the equation to solve the simultaneous equations by substitution over here in black, which is of course underneath the actual equations for these parabolas and lines. And just to show you, when you use this later on, you can do whatever shape you want with it. So once again, looking at the simultaneous equation in the black, you can see that the linear equation is equal to the quadratic equation, and then when we substitute them across, we've got this other line down the bottom, which is the simultaneous equation. Now that equation actually makes a parabola, so let's have a look at that. Okay, so that's what this blue equation is. That is the simultaneous equation being represented in a graph. And you can see that we could move around this line, and we've got things like one intersection here, but if I move it, we can make two intersections or no intersections. And ignoring the intersections between the red and the blue line, you can see that the intersections caused between the red and the green line relate to the amount of x-intercepts in the blue line. So let's do that again, starting off with one intersection, two intersections, and no intersections. So anyhow, that's something for you to think about, but let's go back to OneNote to get into a lot more detail with this discussion. So as I was alluding to in that app, it's not always clear exactly how many intersections there will be. So once again, let's start with a recall to the linear unit. When we're doing the simultaneous equations, we could have one solution, no solution, or infinite solutions. And if we consider infinite solutions as no solutions, we can recall that the hint that there would be no solutions is that the gradient was the same. So in regards to lines and parabolas, if our parabola and line looks like this, now this line on the left, we call it a secant, and it has two solutions. And this line in the middle, we call a tangent, and it has one solution. And we don't really have a name for this one, it's just got no solutions. The two with names relate to some geometric concepts, which I hope you're familiar with, but that one about tangents is going to become super important to you next year, so maybe you want to think about how that occurs. So anyhow, it's nice that we can define the amount of equations by looking at graphs, but how do we know the amount of solutions without drawing graphs? Well, say hello to my little friend, the quadratic formula. You know the one where x is equal to minus b plus or minus the square root of b squared minus 4ac all onto a. You should know it by now. Anyhow, let's make it about simultaneous equations with parabolas. Okay, so once again, for example, we're going to think about y1 equal to mx plus c1 intersecting with y2 equals ax squared plus bx plus c2. And we know that's going to happen when y1's equal to y2. So, as we saw before with the algebra, that means that mx plus c1 is equal to a times x squared plus bx plus c2. And without doing all the steps, seeing we've already done it today, I can now rewrite that as a times x squared plus b minus m times x plus c2 minus c1 equal to 0. So this is true using the quadratic formula when x is going to be equal to minus b minus m plus or minus the square root of b minus m squared plus 4 times a times c2 minus c1, all divided by 2a. Now I understand that looks like a lot of algebra, but it will be numbers in the examples. And by that, what I mean is, when you've finished your simultaneous equation, we'll see that we'll just have a quadratic equation with a and b minus m and c1 minus c2 being the constants in that quadratic. Okay, so they'll just be numbers, so don't need to worry about it, okay? Let's remember, what do we know about that discriminant? Well, the discriminant in this case is equal to b minus m squared minus 4 times c2 minus c1, or the technical term for it is the stuff inside the square root. And as we've covered many times in this unit already, if that discriminant is greater than 0, our quadratic equation has 2 solutions. And if it's equal to 0, we have 1 solution. And if it's less than 0, we have no solutions. And don't forget that in this case, our solutions will be intersections. So if you think about it back to that GeoGebra applet, we're finding solutions to that blue quadratic, okay? Also, please note that these techniques give you the x value. It is really important that you remember that intersections are coordinates. So once you have your x values, don't forget to sub them into the equations to find the y values. Sometimes that's also a great time to check if it's correct by seeing if you get the same y value in both equations. Of course, if you're in a hurry, you can check one, but I do recommend checking 2 sometimes. So there are some other straight lines to think about, and these are y is equal to c or x equal to a. Okay, so our variable is just equal to some constant. So if I was to draw them with a parabola, then we have x equals to a as a vertical line, and y equal to c is this horizontal line. So I'm guessing a lot of you might be able to see that and see what's going on, but I'm going to let you think about x equals a when you pause the video now and work on the building understanding questions in the new book, which translates to questions 2, 4 and 5 in the old book. And then we're going to cover y equals c in the next section anyhow. Make sure you pause that video and do those building understanding questions. I'll see you in the next section. A horizontal line can be described as y equals d. And we know now that the intersection between a parabola and a horizontal line will be where y is equal to d and y is equal to a times x squared plus bx plus c. And really, that's just the same as saying that the quadratic a times x squared plus bx plus c is equal to d. And when we subtract d from both sides, we get a times x squared plus bx plus c minus d equals 0. And we've pretty much got the same parabola, it's just that we've got a new constant. So from this point, you can just solve that new quadratic with the quadratic formula or by factoring. But if you can't factor it first, it really is a good idea to use the quadratic formula to check how many solutions there actually are. And hopefully you realize there could be 0, 1 or 2 solutions. Anyhow, let's get straight into example 14, where we're going to find the intersections of the following parabolas and lines. In part A, we have a quadratic x squared minus 3x and a line y equals 4. So I'm just going to graph these now. Now I know that the line is y equals 4, and that quadratic is equal to 0 when x is 0 and x is 3. So later on we're going to find the value of these intercepts. Not really that much later on, let's just do it straight away, eh? So we know that this is true when x squared minus 3x equals 4, or in other words, x squared minus 3x minus 4 equals 0. Now I can see that minus 4 is equal to minus 4 times 1, and they add up to minus 3. So straight away, I'm going to factor this as x minus 4 times x plus 1 equals 0. And by the null factor law, that's true when x is equal to 4 or x is equal to minus 1. And if we look at the line, y is always going to be equal to 4 on that line, right? So that means that my solutions are x is equal to 4 and y is equal to 4. And the other one is x is equal to minus 1 and y is 4. So we can mark them in on the graph and we're done. Let's move on to part B, where we've got the quadratic x squared plus 2x plus 4 and the line y equals minus 2. And of course they intersect when they're equal, so we'd get x squared plus 2x plus 4 equals minus 2. And adding 2 to both sides, we've got x squared plus 2x plus 6 equals 0. And there's no factors of 6 that add up to 2. So I think we should jump straight into the quadratic formula. And I can see that b is 2, a is 1, and c is 6. So the solutions to this quadratic will be where x is equal to minus 2 plus or minus 2 squared minus 4 times 1 times 6 all over 2. And straight away I can see that discriminant is equal to 4 minus 24, so that's minus 20. And because the discriminant's less than 0, there's no solutions. And I could actually graph these over here. Now the first thing to notice is that y equals minus 2 just goes along here. And for the parabola, I can see that its y-intercept is 4 and its axis of symmetry is at minus 2 on 2, so it's minus 1. And at minus 1, we have plus 3. So therefore the parabola is something like this. Wow, still bad. Anyhow, that's definitely y equals x squared plus 2x plus 4. And as there's no intersections, there's certainly no solutions for that simultaneous equation. Alright, so I do think that's pretty straightforward. So you should really quickly pause that video and do questions 1 and 2 in the new book and question 6 in the old book. And then we'll see you in the next section. Yes, we're looking at intersections between lines and parabolas, but it's also describing a simultaneous equation. Now, y equals a times x squared plus bx plus c1 might describe one situation, and y2 equal to mx plus c2 might be describing another situation. And to find where they're equal, we could use either a graph or algebra. So if y1, and let me mark that in as y1, is equal to y2, then a times x squared plus bx plus c1 has to equal m times x plus c2. And when we put those together, that means that a times x squared plus b minus m times x plus c1 minus c2 is equal to 0. Then we can solve this quadratic to find the x value. Of course, we still need to find the y value related to these values of x. And that's pretty easy by just subbing x into one of the equations. Or 2 if you want to be safe. Alright, let's have a go at example 15, where we'll be solving the following equations simultaneously. And throughout this example, I'm going to use this GeoGebra applet to check our solutions. Of course, once you see it, I'm guessing a lot of you will want to use this as well. Anyhow, in part A, we have a quadratic y equals x squared and a line of y equals 2x. So that means if these equations are the same, then x squared is equal to 2x. And subtracting 2x from both sides, we get x squared minus 2x equals 0. And that's pretty simple to factor because I'm just going to take x out as a common factor and have x times x minus 2. And by the null factor law, that's true when x is 0 or x is 2. And now we need the y component of the solution, of course. So when x is 0, 2x is equal to 0 and x squared is 0. So you can see in both equations there that y is equal to 0 when x is equal to 0. So our solution is x equals 0 and y equals 0. Well, that's one of our solutions. The other one, of course, is when x is equal to 2, 2x is equal to 4, and x squared is equal to 4. So therefore, when x equals 2, y is equal to 4, and that's our other solution. So let's pop over and see that in GeoGebra. Okay, so you can see our applet for this simultaneous equations. So I use that box where the blue writing is for my quadratic and the red one for my line. And sure enough, we see x equals 0 and y equals 0, and x equals 2 and y equals 4 as our two intersections. Alright, let's go back to OneNote. Okay, in part B, we have the quadratic y equals minus 4x squared minus x plus 6, and the line y equals 3x plus 7. So by substitution, I know that these two equations are equal when 3x plus 7 is equal to minus 4x squared minus x plus 6. And 7 minus 6 is 1, and 3x minus x is 4x, and minus 4x squared is 4x squared. So we're left with 4x squared plus 4x plus 1 equals 0. And 4 times 1 is 4, and factors of 4 that add to 4 are 2. So I'm going to break up the 4x into 2x plus 2x, and that gives us 4x squared plus 2x plus 1 equals 0. And taking out the common factors, I've got 2x times 2x plus 1 times 2x plus 1 equals 0. And I've got 2x, and I've got 1 times 2x plus 1. So we've really got 2x plus 1 squared here. Therefore, we have one solution, and that solution is where 2x plus 1 equals 0. And so I can subtract 1 from both sides, so we've got 2x equals minus 1, and divided by 2, so we've got x equals minus a half. And as I said, let's be safe and sub it into both of our equations. So when x is equal to minus a half, the quadratic will say minus 4 times minus a half squared minus a half plus 6, which is equal to minus 4 times a quarter minus plus a half plus 6, which is 11 on 2. And if I sub minus a half into the linear equation, I got 3 times minus a half plus 7, which is equal to minus 3 on 2 plus 7, which is also equal to 11 on 2. So that's pretty sweet. We've got the same answer there for both equations. So therefore our solution is x equals minus a half and y equals 11 on 2. All right, let's have a look at that in the OneNote. So our quadratic equation was minus 4x squared minus x plus 6. And our linear equation was 3x plus 7. And sure enough, we can see the intersection here is at minus 0.5, which is x is equal to minus a half, and y is equal to 5.5, which is 11 on 2, because 5 is 10 on 2. Let's zoom in on that, hey? So sure enough, it kisses the line perfectly. All right, let's get back to our OneNote. Okay, so we're back in OneNote now, and let's get on to part C, where we have the quadratic y equals x squared plus 1, and the line 2x minus 3y equals minus 4. All right, so this is going to require some real substitution, eh? And so the way I'm going to do that is I'm going to write out the linear equation 2x minus 3y equals minus 4, and I've left a bit of room with the y there because I'm going to replace that or substitute in x squared plus 1 for y. Okay, because I've just used this other expression of y from the top and put it here in the bottom. All right, so the next step is to expand that bracket. So we've got 2x and minus 3 times x squared minus 3 equals minus 4. Now I prefer to have my x squared as a positive thing, so I'm going to move everything from the left to the right. So we're going to have 0 is equal to plus 3x squared minus 2x, and minus 4 plus 3 is minus 1. And 3 times minus 1 is minus 3, but also minus 3 plus 1 is equal to minus 2. So I'm going to rewrite minus 2x as minus 3x plus x. Okay, so I'm just setting this up to factor by grouping. So taking out the common factors, we've got 3x times x minus 1 plus x minus 1. So because plus just means I'm multiplying it by 1, I've got 3x plus 1 times x minus 1. And by the null factor law, that means 3x plus 1 equals 0 and x minus 1 equals 0. Or in other words, x is equal to minus a third, or x is equal to 1. Now when x is equal to minus a third, the quadratic is equal to minus a third squared plus 1, which is equal to 1 on 9 plus 1, which is equal to 10 on 9. And the linear equation makes 2 times 1/3 minus 3y equals minus 4, which leaves us with minus 3y is equal to 2/3 minus 4. And if I divide everything by minus 3, I've got y equals minus 2 on 9 plus 4 on 3. And because 4 on 3 is 12 on 9, I've got 12 minus 2 on 9 equals 10 on 9, which thank goodness is the same as the other one. Alright, now when x is equal to 1, the quadratic y is equal to 1 squared plus 1, which is 2. And for the line, we've got 2 times 1 minus 3y equals minus 4, which means we've got minus 3y equal to minus 6. And dividing everything by minus 3, we've got y equals 2. So therefore, one solution is x equals minus 1/3 and y equals 10/9, or x equals 1 and y equals 2. Alright, let's go to GeoGebra and put that in. So our quadratic was y equals x squared plus 1, and our linear equation was 2x minus 3y equals 4. Okay, we're going to need to zoom out to see our solutions here. And sure enough, we can see the 1, 2 there, and minus 0.33 is minus 1/3, and 1.11 is 10 on 9. So once again, we've got them correct, and there's a visual representation of them. Alright, let's go back to the OneNote. Alright, I want you to really take notice of the different methods of substitution that I used, particularly in part C. Quite often some of these answers are going to require that sort of flexibility from you. Okay, but anyhow, at this stage, I think you should pause that video and do questions 3 and 4 in the new book and questions 7 and 8 in the old book. And then you can come back and we'll work on the next section. So as we've already seen a few times, to find where y equals ax squared plus bx plus c1 intersects with y equals mx plus c2, we need to find the x value where ax squared plus bx plus c1 is equal to mx plus c2. And of course we can transform that into ax squared plus b minus m times x plus c1 minus c2 equals 0. And so far we've solved a lot of these using simple factoring. But when you can't use simple factoring, you're going to have to use the quadratic formula. Okay, let's hop straight into example 16, where we're going to solve y equals x squared plus 5x minus 2 and y equals 2x simultaneously. Okay, so this means that we're looking for where x squared plus 5x minus 2 is equal to 2x. And of course that's the same as saying x squared plus 3x minus 2 equals 0, because 5x minus 2x is 3x, right? So let's recall that the quadratic formula is x equals minus b plus or minus the square root of b squared minus 4ac all on 2a. And in this quadratic that we're looking to solve, a is equal to 1, b is equal to 3, and c is equal to minus 2. So therefore in this case, we're looking for x that's equal to minus 3 plus or minus the square root of 3 squared minus 4 times 1 times minus 2, all divided by 2. So cleaning this up a bit, 3 squared is 9, minus 4 times minus 2 is plus 8. So we're left with minus 3 plus or minus 9 plus 8, all square rooted, all over 2. Therefore, the solutions to this quadratic is where x is equal to minus 3 plus the square root of 17 over 2, or minus 3 minus the square root of 17 over 2. And remembering that that linear equation is y equals 2x, when x is equal to minus 3 plus the square root of 17 over 2, then y equal to 2x is minus 3 plus the square root of 17. And similarly, when x is equal to minus 3 minus the square root of 17 on 2, y equal to 2x is equal to minus 3 minus the square root of 17. Okay, so they're the actual answers. So if you were to graph them, I would leave them in their exact form, particularly when you note them down. but it's always good to use a calculator. So let's practice that with one note. All right, so minus 3 plus root 17 on 2 is around about 0.56. And minus 3 plus root 17 is 1.12. And minus 3 minus root 17 on 2 is minus 3.56. And minus 3 minus root 17, minus 7.12. Now, there really was no need for me to do that, but I'm actually doing that to check ahead of time before we look at GeoGebra, because they always write it in 2 decimal places. All right, let's switch over to GeoGebra. So the quadratic equation in this question is x squared plus 5x minus 2. And the linear equation is y equals 2x. And I'm going to have to zoom out here. And sure enough, we see 0.56 and 1.12 for one solution, and minus 3.56 minus 7.12 for the other solution. So we're getting pretty good here, right? Okay, let's go back to the OneNote. Okay, I'm pretty hopeful that that big algebraic statement seems a lot easier when we use actual numbers. Alright, but at this point you should pause that video and do question 5 in the new book and question 9 in the old book. And then when you come back, we'll work on the next section. So when we're solving a quadratic equation like y equals ax squared plus bx plus c, the solutions are where x equals minus b plus or minus b squared minus 4ac divided by 2a. And of course the determinant, which is equal to b squared minus 4ac, tells us exactly how many solutions there are. Of course you know this already, but I just want to note it down for this section, okay? So if the determinant is less than 0, then there's no solutions. If it's equal to 0, then there's one solution. And if it's greater than 0, we've got 2 solutions. And the reason why this is relevant is when we're solving a quadratic and a linear equation simultaneously, with some quadratic equal to a times x squared plus bx plus c, and a linear equation equal to mx plus d, if y1's equal to y2, then ax squared plus bx plus c equals mx plus d. And with a little bit of algebra, that means that ax squared plus b minus mx plus c minus d is equal to 0. And so we've got this new looking quadratic equation here, but we can still do the same thing as we've done with the previous ones. But in this case, we've got these new constants here, a, b minus m, and c minus d. So to figure out how many intersections there are, then the discriminant here will be equal to b minus m squared minus 4 times a times c minus d. And of course the intersections between those two lines is the solutions to this quadratic equation. Now, as we saw in the last section, this looks like a lot of algebra, but it's going to be a lot simpler to show when we actually use numbers. So while those things might be good for you to take your notes down, I just think we should jump straight into example 17, where we're going to determine the number of solutions to the following quadratics. Okay, in part A, we've got a quadratic y equals x squared plus 3x minus 1, and a linear equation y equals x minus 2. So when they're equal, of course, x squared plus 3x minus 1 is going to equal x minus 2. And when we neaten that up, that means that x squared plus 2x plus 1 equals 0. And I can see that's a perfect square. So I know there's going to be one solution. So we expect the determinant to equal 0, right? But let's just go through the motions to prove that is the case. All right, so in this case, we've got a is equal to 1, b is equal to 2, and c is equal to 1. And b squared minus 4a squared is equal to 2 squared minus 4 times 1, which equals 4 minus 4, which is 0. And as our determinant is 0, there has to be one solution, which is what we expected, right? So let's have a quick look at that in GeoGebra. Okay, so the quadratic in that case was x squared plus 3x minus 1, and the linear equation was y equals x minus 2. And you can see it's not working because I've still got a 5x there. I don't know why it didn't fix. Let me make that 3x again. That's better. Here we can see there's just one solution, and while we didn't work out what that solution was, we can see it's -1, -3. Alright, let's go back to the OneNote and move on to part B, where our quadratic is 2 times x squared minus 3x plus 8, and the linear equation is y equals 5 minus 2x. I sort of want to go straight to the GeoGebra, but I'll do the right thing by you guys and go through this algebra. Alright, so these equations are equal to each other when 2x squared minus 3x plus 8 is equal to 5 minus 2x. If I subtract 5 from 8, I'm going to get 3, add 2, I'm going to get minus x. So therefore our answer is 2x squared minus x plus 3 equals 0. And we've got an a of 2, a b of -1, and a c of 3. So that means that our determinant is -1 squared minus 4 times 2 times 3, which is equal to 1 minus 24, which is minus 23. And clearly minus 23 is less than 0, so as the determinant is less than 0, there are no solutions. And once again, let's have a look at that in GeoGebra. So in this case, we had y equals 2x squared minus 3x plus 8. And our linear equation was y equals 5 minus 2x. And if I zoom out, sure enough, there is no intersections there. Alright, let's go back to the OneNote. Alright, so that's the end of this example. Pause the video right now and do question 6 in the new book and question 10 in the old book. And then when you come back, we'll summarize this lesson. Okay, just one thing before I start to summarize this lesson. I hope you noticed how helpful that little applet I made was. Here's the link to it. You can look this up in GeoGebra. And I think you'll find that very helpful to work through all parts of this unit, but in particular, the one we're doing today. This lesson brings our unit to a close. And throughout this unit, you've learnt ways to factor quadratics, as well as knowing how many solutions there are. You've learnt how to use these techniques to graph quadratics with parabolas, and you've also learnt how to solve real-world problems with quadratics and parabolas. And finally today, we've learnt how to solve simultaneous equations that involve quadratics. So it's really been a huge unit, and you should be really proud that you've gotten through this. But make sure you go back and check through each of those skills, and that you should be confident to be able to perform every single one of them. They are vital for what's coming ahead. That's this year and next year, okay? But I also want to say that in today's lesson, we touched on tangents, i.e. for this parabola here and this line, they just touch each other, right? And these are the ones there was only one intersection. Well, next year you're going to find out how much those tangents do tell you about the parabola. And so it's really important for next year. So I really hope you took notice there, and maybe you should be thinking about how could I mess with the quadratic formula to ensure that I have a tangent. Okay, so in today's lesson, a successful student will understand how a line can intersect a parabola at 0, 1 or 2 points. Be able to find the points of intersection of a line and a parabola by using substitution. And finally, know that the discriminant can be used to determine the number of points of intersection of a line and parabola. Alright, well done all. We'll see you in the next lesson, or the next unit, whether that's in class or in the next video. Bye.